Hello, and welcome to this example on eccentrically loaded columns. Now, this example assumes that you've already reviewed a section in a textbook on eccentrically loaded columns, specifically in Beer and Johnston, that you have reviewed section 10.2. This might not make a lot of sense. So what this example is a wide flange column. It's a W10 by 39 out of steel, so E is 29 times 10 to the 6 psi. It's a cantilevered column, so it's fixed at the base and free at the top, and it's a 10-foot long column. Now, the load is not applied concentrically through the centroid, but rather is offset with an eccentricity of 1/2 of an inch. And we can see that that eccentricity will cause a moment about the z-axis. So this is going to rotate about the z-axis. Because of that, we know that there'll be a moment about the z-axis, so we're concerned with both the I value and the S value around z, not I sub x. It's weak axis bending. And so what the question wants us to do is to determine the magnitude that we can apply, the magnitude of P, that we can apply if there is a 0.6 inch horizontal deflection at the top of the column. So what P would cause 0.6 inches of lateral movement, and then the maximum corresponding stress to go with that. And so immediately we can go right into the tables and look up our values, and because we established this is bending about the z-axis, I pulled out the moment of inertia and the section modulus about the z-axis, and of course the cross-sectional area, which we can see there. Now, quickly looking at how this will deflect, here's a side view with the z-axis pointing out towards us, and we can see our eccentricity of P. The dashed lines are showing the web that wouldn't be hidden from this side view. And if we drew the deflected shape, this is really exaggerated. There's that Y max value we're talking about, and I'm drawing from centroid to centroid. P would still be offset. And because this is a fixed column, we know there's a reaction at the base, B, and that reaction moment is going to be the maximum moment along the length. So that's going to cause the maximum stress. And that has to be a function of both P times E. But then once I deflect, I'll also have P times Y max. So I'm getting a snowballing effect. And while we're here, as we look at our deflected shape, we can see that we're only getting half of that sine curve that the Euler's buckling equation was developed off of. So our effective length needs to be 2L. So let's take a quick look at some things we already know out of section 10.2 in the Beer and Johnston text on eccentric column loading behavior. So we can still use P critical as our standard pi squared EI over L effective squared. And we've established that to get that Y max value, we actually can take the eccentricity value E and multiply that by the quantity of the secant of pi over 2 times the square root of P over P critical, and then subtract 1 from that. So we also note that this is a combined loading situation. So we're not going to load this up to P critical because of that additional moment that the eccentricity kicks in. We're not going to get to a P critical value. We would bow out before that and have too much excessive deformation simply because that moment that we're causing, and then as it overturns, it just causes more moment. We get so much deformation, we have to keep the load down. Otherwise, we wouldn't be a functional member, so we will not get to P critical. And so our combined loading gives us P over A plus MC over I would be the stress that our member's experiencing, and we've already established that our moment is a combination both of the initial P times eccentricity, and then once it starts bowing, we also have to take P times Y max. So let's go ahead and rewrite that Y max equation that we're able to get out of section 10.2 for the P over P critical ratio, because our goal is to find what P causes a Y max of 0.6 inches. And we can find P critical from our standard P critical formula. And so what that's going to look like is we can immediately divide the E from the right side and divide Y max by E, and then move the 1 over to the left side of the equation. We can also note that 1 is nothing more than E over E, so we can rewrite the left side as Y max plus E over E, and that's just going to be equal to the secant of pi over 2 times the square root of P over P critical. And if we also note that the secant is nothing more than the inverse of the cosine, we can then just flip both sides of the equations, so we'd have E over Y max plus E, and then the cosine of pi over 2 times P over P critical. So we're just going to take the inverse of both sides. And then we can actually take the inverse cosine or arc cosine of both sides of our equation. That then keeps the pi over 2 outside of the cosine, and then we can multiply both sides by that. And what we would end up with, as we can see here, is once we take the inverse cosine, we can then multiply both sides by 2 over pi, and then we need to square both sides, and we're left with our P over P critical is the 2 pi times the inverse cosine or arc cosine, same thing, of E or eccentricity divided by Y max plus our eccentricity, and then the entire quantity squared. And we know everything that goes in that formula, so we can actually start plugging values in. So we'd have our 2 pi times the inverse cosine of our eccentricity, which is a 1/2 inch, divided by our 0.6 inches plus a 1/2 inch. That quantity squared, and it turns out that's 0.489, and so P is just 0.489 times P critical. And P critical, we know that's our standard equation, so if we plug in our 0.489 times pi squared times our 29 times 10 to the 6 psi for E, our I we established is 45 inches to the 4th. And then we use our L effective, so that's 2 times, and we'll use 120 inches instead of 10 feet, so we immediately convert to inches and our units work out. And we're actually going to find that we have 109.4 kips is the axial load that's going to cause 0.6 inches of displacement. And I have to tell you, ladies and gentlemen, that on tall buildings, on any sort of freeway sign or whatnot, sway at the top, that lateral movement, that's typically your controlling factor, not going to be buckling. And so now let's find out what kind of stress is caused by that load and that snowballing, overturning moment that comes from the eccentricity. So we established that already our sigma is P over A plus MC over I, and just to simplify things, instead of having to look up and find out what C is for this shape or the depth and take the half of that, remember we can also use the section modulus. So MC over I is the same thing as M over S, and we were able to pull that right out of the table. And don't forget, we also know that the moment max is PE plus PY max. So let's just start plugging things in. So we'd have our P over A, 109.4 kips divided by our 11.5 inches squared. And then we'd have our P, our 104.9 kips, times the eccentricity, 0.5 inches, plus the lateral displacement of 0.6 inches, and all of that divided by our section modulus of 11.3 inches cubed. And that's going to give us 20.2 KSI as the max stress acting on our column. So that's solving an eccentrically loaded column. Remember, we're really not going to get to buckling on these. It's going to be lateral displacement that controls. And so a lot of it is just knowing how to manipulate the equations. Thanks for watching.